We're going to learn about what is a power series and also motivate and also find the so-called radius of convergence for these kind of series. So, what is a power series? A power series is just a series in this form. Notice you've got a C sub n down here. Now the boxed setup is known as a power series about the point x equals 0. So it's sort of like a more general version of a Maclaurin series because C sub n doesn't have to involve derivatives. In equation 2, notice I've got x minus a all to some sort of power. This is known as a power series about the point x equals a. So they're kind of like Maclaurin series, kind of like Taylor series, but not, in the sense that in here, the CNs for a Maclaurin series are given by this special setup. They involve derivatives and factorials. And similarly with 2. 2 is a special class of, in 2, if Cn equals the boxed equation down the bottom, then we get a Taylor series about the point A. Now, we've already seen that we can do reasonably interesting things with convergent series. We can integrate them, we can differentiate them, maybe we can shift them around and obtain other useful things. What we're going to talk about in this lecture is the idea of convergence. This is really, really important. So the basic idea a convergent power series, well, you can do stuff with it. You can work with it. You can differentiate it, integrate it, add two things together, two convergent power series together. So let's look at a real simple example, this power series here. Now you may be looking at this and go, oh, hang on, Chris, I know this series. What kind of series is this? It's a geometric series, right? But what I'm going to do is just show you simply the basic ideas that we're going to learn today for this example. I know you can work with this in other ways, but let me just show you. So just suppose, well, first of all, notice we've got an x here. So really, this whole series is a function of x, big F of x. And what we're interested in asking is what values of x give this f of x meaning? What's the domain of this big F? What's the domain of that power series or that function? If we know the domain, then we know a set of points where we can work with this power series and do things with it. So let's actually just go, just sub in, say x equals 0 in here. Do I get a finite number or an infinite number? Well, the first term's going to be 1 and all the other terms are going to be 0, right? So it's a finite number. So f of 0 equals 1, it's defined. So in other words, 0's in the domain of this. What about x equals 1? Is that in the domain? Substitute in, and you're going to get some sort of series like this. Okay? This series converges, and we can actually work out it converges to 2. So that means that x equals 1's in the domain of this. Let's try something else. X equals 3. If I sub in x equals 3, what happens? Well, if you look at that sum, again, it's a geometric series, you're summing up 3 over 2 all to the n. So that diverges to infinity. So f of 3's not defined. 3's not in the domain of this function. What we'd like to do is not just sub in values, we'd like to determine some way, some sort of method without just subbing in. So that's the basic idea of the remainder of this lecture. Now, it relies on something you already know. That's the really good thing about these ideas. They rely on something you already know. Now, let's just go... I guess I can write it down here. Suppose we have a function defined via this power series, right? Now, we know from basic geometric series that this series converges for x between -2 and 2. So what we have there is a little interval that's the domain of this function. Now let me just sort of draw a picture for you. This interval is known as the interval of convergence for this particular function. You can see I haven't included the endpoints in the interval, and in particular, there's a little radius involved. So if you look at half the interval, you get some sort of radius of convergence. And this is common for the power series that we're going to look at. They've all got a radius of convergence and an interval of convergence. It might only be a point, might be the whole line. But different power series converge for different things, different values of x, different intervals. So, the convergence of some power series is described by one of the following three possibilities. Well, let's look at the second one first. The series converges for all x, so in other words, the radius is the whole real line, or the interval is the whole real line. The series converges at one point only. That would be the centre of that interval, nowhere else. Or, and most commonly, you actually do get this setup where there's some positive number r such that inside this interval you get convergence, outside the interval you get divergence, and on the boundary, on the endpoints, well, you might get convergence, you might not get convergence. So this is quite common to all these kind of power series we're going to see. So how do you come up with this interval of convergence, this radius of convergence? Well, stuff you already know. That's the nice thing about it. It is basically an application of the so-called ratio test. Okay, the ratio test. Now, up there I've got the nth root test. Just forget about that. That's not in the course, so just you don't have to worry about that. So, we're going to be asked to come up with this radius of convergence. When you see this, think of the ratio test. You look at the limit of a ratio. Is the ratio less than 1? Well, if it is, then you've got convergence. The second point involves the end points of the intervals. You've got to test those as well. And thirdly, you'll get some sort of, I guess if this is finite, you'll get some sort of place where the series or the power series diverges. So let me give you an example and show you how it's done. We're going to return to our example of this geometric series, again, because it's kind of simple. Think back to the ratio test. Okay, here I've got Bn instead of Cn. It doesn't really make a difference. You look at the ratio of these two things and the limit, right? So here, B sub n equals 1 on 2n, and so B sub n plus 1 is just this. Now, the only difference between this solution and the one we did a in the previous subsection is that there's x's hanging around. Okay, there's x's hanging around. Now you'll see that you can cancel off these x's. You're going to be left with 1x, right? You can also see that I can cancel off some of these powers of 2. I'm going to be left with 1/2. Now look at this limit for a second. That limit involves n, but where are the n's in there? There aren't any. So the limit of that's not going to change, right? There's no n's in there. So we need to think, okay, I've calculated my rho, the limit of my ratio. When is this less than 0? What x values will make this less than 0? Well, less than 1, strictly less than 1. Well, when x is between -2 and +2, that underlined inequality will hold. And outside that, that's when rho will be greater than 1. Okay, here. When x equals 2 or x equals -2, you're not sure what happens. Now, at x equals plus or minus 2, the ratio test fails because the limit's 1. You don't know. It doesn't tell you anything. That's a real basic example of how to apply the ratio test to these power series. So let's do an example, another one, and see how we go. So something that you might get tested on in end session. Here's a power series. Here the Cn is 1 on n factorial. So C sub n plus 1 is just 1 on n plus 1 all factorial. Now, here's a good question. Does that function, that power series, look familiar to anyone? Yes, it's the power series for the function e to the x. You're not supposed to know that, but if you recognise it, great. It doesn't affect what we're going to do here. Let's go through and apply the ratio test. So we want the limit of the following ratio. Now a little bit of algebra is going to come into the mix here. We need to cancel stuff off. Now because I'm dividing, I guess, 2 fractions, I'm going to multiply by the reciprocal. Now what we want to do is cancel off. I can cancel off some of those factorials and some of those powers. So let's do that. Okay, so if I just use this little setup over here, I can cancel, and I'm going to get down to something like this. Now the limit that we're taking, n's going to infinity, it's got nothing to do with x. So I can shift that x out and rearrange a little bit. All right, so what's my limit going to be? Huh? 0. Now, that's true. It's 0 no matter what x is. For any finite number x, that limit is always 0. So the limit, our rho, is I guess it's 0, and so it's less than 1 for all x. So what does it mean? By the ratio test, right? By the ratio test, does it converge or diverge? Converges, right? So if it's the whole real line, what's our radius of convergence then? It's infinity, right? Yeah. Our radius of convergence is just infinity. Okay, so with that particular example, you don't have to worry about the endpoints because it's the whole real line. It's got no endpoints. So you don't have to worry about it. So what does it mean? For every x you plug into that starred power series, you're going to get some finite, some meaningful value out of. Right? And in fact, you're going to get e to the x for every value of x. Now you're not supposed to know that, so don't worry if don't worry too much about that bottom line. Questions for that example? It's a good example because it builds on stuff you already know. Ratio test. Yes.
Shouldn't you say R approaches infinity because infinity is not
Yeah, I'm abusing the notation there. Yeah. So, I mean, for this, what's the radius of the real line? I mean, you're abusing your mathematics there. Like, yeah. I mean, it's okay. It's okay. If anyone gives you trouble, just say Tisdell said it was okay in lectures. Okay, underline it. All right. Yes. Huh? Why? Because you don't know if x is positive or negative, right? Because x could be negative, could be positive. You don't know, right? Any other questions? So that's a good example of something you might see in the standard that you might see in the end session. So here's something slightly more difficult. This is a power series, and A equals 5 here. A equals 5. So now, there's not much difference between the method for this one and the previous one. You just got to be careful with the algebra when you're cancelling off. So consider, please. The limit of the following ratio. Okay, note instead of just x here, x to the n plus 1, I've got x minus 5, all to the n plus 1. So again, I can cancel off. In fact, some of you may want to skip this step. I'm going to cancel off here. I'm just going to have an absolute x minus 5 left. Now, what about these guys here? Well, again, I'm multiplying by reciprocals. So I'll get something a little like this. And it's just a matter of simplifying. Now, those minus 1 to the n and minus 1 to the n plus 1s, can anyone tell me why are they going to disappear? Why can't I just get rid of these straight away, this and this? or just absolute values. If you take the absolute value, it's got to be 1, right?
I think that's how it's also.
Sure, yeah, sure. Yep, that's fine as well. And why can I take the absolute values away from the n and the n plus 1? Well, because n's large and positive. So I can actually get rid of those absolute values and come up with something like this. So what's the limit? Limit's going to be 1. So now all I really need to do is find out what x values make this strictly less than 1. Okay, so this is our limit of our ratio. We want to find the x values that make that row less than 1. Less than 1. Yeah. So how can we make this less than 1? Well, just choose, choose an x value. Well, x equals 5 will make this less than 1. So let's form some sort of interval. So absolute x minus 5 is going to be less than 1 when this is true. So all you need to do is rearrange that, add 5 to the bottom right-hand side, and rearrange. So if I add 5, I'm going to get this. That's my interval. That's my interval. So for all x points in that interval, my power series converges. It makes sense. It's well defined. We can do things with it. So let's make a conclusion. Our power series converges for all x in this interval. So who can tell me what's the radius of convergence going to be for this problem? 1, right? Because if you draw this interval, just look at half the length of the interval, right? Now, what happens at x equals 4? What happens? Well, let's find out. So let's go up here, plug in x equals 4. So this is one time when we do have to actually just sub in. So that's going to be minus 1 to the n all over n. All right. What's going to happen to these two things? Well, it's a squared, so they're just going to go to 1. What does this series do down the bottom? Sigma 1 on n. Does it converge or diverge? It diverges, right? So in other words, f of 4, well, it's got no meaning. It's not well defined. What about at x equals 6? So I go up here, plug in x equals 6, and I'm going to get something like this. Times 1 to the n, which is just 1. What about this series down here on the bottom? It's an alternating series. Does it converge or diverge? It converges, right? This is an alternating series that converges. Leibniz test. Or AST. I won't put in all the details. So what does it mean? It means these points are in the domain and this point, but not this point because this series diverges. So you have a bit of a weird situation where one of the endpoints is in the interval, the other one's not. Questions? As you can see, there's a few steps to these problems. Yes? Sorry, say again? Yep. Why didn't we start with Leibniz test? Good question, because Leibniz test is for alternating series only. And this may not be an alternating series, right? Because you don't know where x is. Okay, so sure, you've got the -1 to the n, but you don't know where x is. So that's a really good question. Any other questions? Again, fairly standard example. Hopefully you should be getting into a bit of a groove now. Apply the ratio test. Find some sort of interval. Look at the radius of convergence, then test the endpoints. That's it. That's as simple as I can make it. Okay, ratio test, form some interval, test the endpoints. That's it. So, let's apply the ratio test. It's the limit of a ratio So all we have to do is somehow simplify and take the limit. Now you can see the powers are going to cancel pretty nicely. And I'm going to get n plus 1 all on n. Now I don't need the absolute values because the limit's going to positive infinity. So what's the limit going to be? N plus 1 on n, it's going to be 1. So we get down to this. Now this will be less than 1 for certain values of x and greater than 1 for other values of x. So here's our little interval. X is between -1 and +1. Whoosh. So we know that we have convergence for at least the open interval -1 to +1. So what's our radius of convergence then? If that's our interval, what's our radius of convergence? 1, right? So the last thing we've got to do is test our endpoints. What happens at x equals 1, x equals -1? So I plug in x equals 1 there, and I get this. Now, who can tell me, does that series converge or diverge? It diverges. Why? Huh? Man, put them away, man. Oh. Does it converge or diverge? Come on, you should know this. That bottom series. Huh? Diverges. Do you know why? You're absolutely right. Do you know why? Yes! Nth term test. You rule. All right. Nth term test. It's the simplest one, right? Diverges. See, that's pretty good when you can juggle, try to hide it, and still bring up the nth term test. I'm loving it. I'm loving it. You're on fire. The nth term test. And what about x equals -1? So let's go up here, put in -1. Does that converge or diverge? Yes. Why? What did you say before? That's it, right? This cannot go to 0. It just goes, you know, it'll oscillate and just get bigger and bigger and bigger each time. It can't go to 0. So again, this diverges by the nth term test. Thus, what's the convergence of this? The domain is just the open interval. Well done. Now, I've got to say, it's not a guarantee, but I almost guarantee you something like this on your exam. Okay, not a money-back guarantee. Questions? Name the ratio test. Okay, name it. Write down your radius of convergence. And then test the endpoints. Now, Now, I've already talked about this many times. If you have a convergent series, you can do stuff with it. Okay? This basic idea says if you have a convergent series, then for all x points that make the series make sense, you can differentiate it and form new series. You can also integrate, provided you're in the interval of convergence, okay, in both theorems. So let me give you an example of here's one I started earlier. Now this looks strangely like the one we did yesterday, and people were going, "Oh, what about the constant of integration? What about the constant of integration, guys? What about it?" Go. It's all right. It's all right. No. People were worried, okay, and I must admit I did gloss over it a little bit, okay. Let me show you why it's all sound and the constant of integration is all okay here. This is a geometric series. We know we can write it as this for certain values of t, right? T in the interval of convergence. What I want to do, though, is relate it, and by log here I mean natural log, of course. I want to relate it somehow back to this. Now, if I replace t with minus x, I can come up with this. And that circled thing, when I integrate it, will give me log 1 plus x. Okay, so this is very similar to the example that we did yesterday. So, we have an idea that we can just integrate and differentiate convergent power series. So let's just do this. Let's integrate here and each term in here, keeping x between -1 and 1. So on the left-hand side I get log. On the right-hand side I get a bit of a mess, but don't think it's too weird. All I'm doing is I'm moving the integral sign inside and then just integrating the powers. You don't have to really worry about expanding the sum or anything like that. But here we've got a constant of integration. Okay? I didn't put in the last one. Can anyone tell me how can we find the constant of integration? Yeah, let x equal 0, right? Because all of these have got to be 0, right? That's got to be 0, so C's got to be 0. So in other words, the constant of integration is just 0. Oops. Now, if you want to relabel that, make the instead of having x to the n, go to x to the n plus 1, go to x to the n. That's up to you. Questions? Yep. Yeah, I would. Okay, that's a good question. The question is, what happens if I got that in the exam? Would I really have to go through and justify the constant of integration being equal to 0? Probably. You'd certainly have to say something. Even if you didn't have to go through and find, plug in everything, just say, look, the constant of integration is 0 here, which may be checked by plugging in x equals 0. You don't have to do the calculations.